this or not? I'll try it anyway. Okay, so it's an extraordinary privilege to be here celebrating Asa's birthday. Compared to all of the other guests, I'm a relative newcomer to knowing him. The first time I met Asa was at this workshop in Crete in 2009 on ADS, CFT, and its applications to kinetic physics. So let me tell you, at this stage, I was 1 year into my postdoc, and at this workshop I was completely out of my depth and had no idea what was going on. And actually, even in the subject now, I still would say that I struggle. But what was really nice was that Asa was the one theorist that was not only willing to explain some of these concepts to me very simply, but also willing to listen to my details on my experimental data. So I was extremely grateful for that. Something that stands out to me in this conference was, so I'm half Greek, my father was visiting me in Crete at the time. And so within a few hours of meeting Asa, he was also meeting my parents, which I realize now from this perspective might have seemed like I was coming on a little strong. But in any case, he even tolerated me, and since I've come to Asa still with some of my most difficult problems. Which brings me to today's talk, and I would say that this is probably one of the most interesting and also most difficult problems that I've worked on, but I think it plays to some of your interests for the better part of, I guess, 30 or so years, certainly more than 20 years. And that's to do with the nature of the Fermi liquid state or the non-Fermi liquid state in high TC superconductors, cuprates, iron connectides, and other strongly correlated systems. So the title of my talk is going to be looking at a novel relationship between the magnetoresistance and the resistance versus temperature in some high TC superconductors, specifically focusing on this iron connectide system. But the basic problem relates to the age-old problem of T-linear resistivity. So the outline of my talk is as follows. I'm just going to have 4 very brief parts. I realize I'm the last talk before coffee, so I'll try and make it as gentle as possible. But I'm going to give you an introduction to why I think this problem is interesting, the system itself, and then straight to the data. This paper recently, our work was recently published last month, just a bit of advertising. Okay, so let me try and tell you why I find this problem interesting. I worked on this problem, or I first was interested in the problem of T-linear resistivity when I was a postdoc at Bristol with Nigel Hussey. And even then, even though I knew that this problem was extremely interesting, I had a lot of trouble explaining why I thought it was something useful to study. And at the time I was reading Richard Feynman's The Character of Physical Law, and I came across this quote, which I think pretty much summarizes why I think this problem is interesting to me and to a number of you in this room. And that is, how do we know that the pieces of the jigsaw puzzle are really all part of one yet incomplete picture? And the problem is that we're really not sure, and this of course worries us a little. But we can take some encouragement from the fact that we see some of these characteristics commonly in several pieces. So here's the first piece of the puzzle. This was a resistivity curve for lanthanum, or strontium-doped lanthanum cuprate taken by Takagi back in 1992. And the basic observation is as simple as it could possibly get. You just have a linear resistivity as a function of temperature for many decades in temperature. Now, as simple as this observation is, it turns out that it's actually very difficult to explain. And more importantly, it's seen in a number of different systems. So another example would be strontium ruthenate, which is not a superconductor, but it's another one of these strongly correlated, presumably non-Fermi liquid metals. What you're looking at here is, again, the same kind of data, resistance versus temperature, but now cooled down in a constant field. So in the red curve, you have the zero field curve, where you see a very strongly, or what appears to be a T-squared resistivity, and then as you attune the magnetic field, to some magic number, you end up getting to the purely T-linear resistivity, which is what is thought to be a critical point. I'll get to a little bit of that in a minute. But the basic idea is that you can plot this data taking the exponent of the T-squared to T-linear resistivity as a function field, and you can plot it as this color plot. And I'll be showing you a couple of these plots in the next few slides, so it's useful to get familiar with it. But what it basically shows is that you can have a crossover from T-squared resistivity to T-linear resistivity back to T-squared as you tune the magnetic field. Now, this kind of behavior is seen in a number of different systems, not just the iron connectides, the strontium ruthenate, terbium, rhodium-2, silicon-2, again with a similar kind of plot here. And also the cuprates are no exception. And the basic question is really what's driving this crossover from the T-squared resistivity, which we commonly associated with Fermi liquid-like behavior, to the T-linear resistivity, which seems to happen at some magic non-thermal parameter values. So that might be doping in the case of the cuprates, it might be magnetic field in the case of strontium native terbium rhodium-2, silicon-2. So the essential, I would say, presumption, or I guess the one that motivated me to look into this physics, although it's by no means conclusive, is that this might be indicative of some quantum critical physics. And the essential, yeah.
Well, when you graph,
there's
also a constant term. So the constant term is
the rho naught.
Even when we alpha goes to 0. Yeah. So in all of these graphs, the constant is 0 when you get to 0.
No.
It's no.
No. You often have an offset, which would be a residual term. Yeah. I mean, that's a good question. It's often associated with the residual resistive inelastic resistivity term, and this would be what we call the inelastic term, simply because it's the way it's a function of changes of energy, right? And this would be the zero temperature term.
But then it would make it non-analytic at 0.
That's right. Yeah. But I'm just talking about experimental observations, and this would be your fact, right? So whether it's non-analytic or not, in terms of the conception of it, I mean, I would leave that up to the theorists. The observation certainly does.
Can you tell us how large the rho naught term is relative to the others in the experiment?
So I would rather get to my data, and and then you can see what rho naught is exactly in that situation. So, but just one concept that I want to communicate from the beginning, and of course it's more familiar to a lot of people in this community than in others. But it relates to, for example, Subir's talk yesterday and a number of other talks. But the essential idea is that because there's only one energy scale that can that goes into the scattering rate, it's often thought, or at least associated, that T-linear resistivity going down to the lowest temperatures is indicative of a quantum critical point, namely a point in the phase diagram where all other energy scales vanish. And the basic idea is that then there's only one energy scale that can possibly set things like the lifetime of the quasi-particle, and that is, of course, temperature. Now, there is some sloppiness to this argument, and it's related to a question of Phil's to Subir yesterday, which was, well, do we know that the scattering rate is exactly going to be what we see in the resistivity? Because, of course, resistivity, what we measure is the momentum relaxation rate, and not necessarily the quasi-particle lifetime, which are not always the same thing. But nevertheless, ignoring that fact just for now, the basic idea is has often been to associate the observation of T-linear resistivity with the presence of an underlying critical point. Okay. Now, if this is to be true, then in analogy with what we know of classical critical points, then we expect scaling forms and scaling relations from here in the data, and that's going to be something that's going to be of importance for this talk, specifically if we look at the resistance of the function magnetic field. Okay, there's one other thing that I want to point out, which I think is very interesting. So let's take the resistivity versus temperature, and you know it's linear, so it has a very specific gradient. This is the alpha kBt. Let's say you could convert resistivity into scattering rate, into a lifetime. Let's say a derivative model, or you have some way of taking account of density of states, and you did this for a number of different materials, then you would have what the prefactor alpha is to kBt. So you'd know exactly what the coefficient was relating the energy scale associated with the lifetime with the energy scale associated with temperature. And this is what Andy McKenzie did fairly recently, which in a literature review back in 2013, where they did this for a number of different materials, ranging from heavy fermions through to cuprates, through to some other strongly non-correlated materials. And they figured out what this prefactor alpha. Now, some of you might already be familiar with in this room what that value might be, but it turns out that for a number of different systems, that number is 1. In other words, there seems to be, on average, an exact equivalence within a factor of 2 or 3, it turns out, but a pretty close equivalence of the energy scales associated with the scattering rate itself and the energy scale of temperature. And this is a highly non-trivial effect. There's no reason that you might expect this kind of relationship or this kind of exact equivalence to occur unless there was something very strange going on, for example, that there were no other energy scales in the system. So this was kind of unusual, and I think it's pretty unique. So that's a really good question. So basically you have to convert resistivity into h bar over tau. So the simplest way to do it would be to take a Drude model, which of course would be wrong, mostly. But the way they did it was a little bit more detailed, where they actually have to take the Fermi surface size and the density of states from some calculation, and then they use that to convert resistivity to scattering. So they've been a little bit more careful than just taking a Drude model. But yeah, that's an essential point. But I would say it still seems like an incredible accident doing that calculation over and over again. You still end up having the same kind of coefficient.
So we use band theory to get this.
Yes, pretty much.
I don't think there's another experiment from the Haas and Alpha.
So there is experimental data, but you don't get the density of states from, I mean, I guess you can get the effective mass, and then you get, so you can get the, assuming, you still have to assume more or less a free electron-like, dispersion, that's right. But yes, you can, something you can get the Haas alpha effect, which gives you the Fermi surface size and the effective mass. Okay. So now let me take you to, so that's kind of the motivation for the physics. I think there's something intrinsically interesting going on. You see this behavior over and over again, which is, I think, why it gives us some hope that there's something universal going on. So in order to motivate the end result, let me tell you a little bit about the specific material. So we'll just zoom in a little bit here. So this is another high TC type material. It has a similar kind of phase diagram that you're familiar with from recuperates. Here, temperature versus doping. Doping in this case is not exactly just adding charges like you would in the whole doped or electron doped recuperates. What's going on here is that you're isovalently swapping arsenic for phosphorus. And even though those exist in the same column in the periodic table, the basic idea is that you're applying some kind of chemical pressure, and as a result, doing all the same kinds of things that you see as a function of doping, namely suppressing the antiferromagnetism as a function of phosphorus, and then giving rise to a superconducting film, just like you do in the other parts of the phase diagram. And it turns out that around this critical part of the phase diagram, your optimal doping, you have very strongly T-linear resistivity crossing over to T squared as you go close to the overdoped part of the phase diagram. And that was observed by Matsuda very early on when they discovered these materials with the were an ionic analog. Okay, so this would be what the raw data would look like. Strongly T-linear near optimal doping and strongly T-squared in the overdoping. Okay, so let me take you to my data now. So the initial motivation for this was to try and see what the physics of the normal state was by suppressing the superconductivity with magnetic field. But we realized very quickly that there was actually physics happening as a function of field as well. Okay, so here is the resistance versus temperature for a typical resistivity curve. This isn't exactly on optimal dope, so it's not perfectly linear all the way to TC. But what you see is in high temperatures, you have very strongly T-linear behavior, and then at some lower temperature, you cross over with a little bit of curvature to some presumably T-squared-like behavior. Okay, so almost all of the data that you're going to look at looks a little bit like this. Here's what the magnetoresistance looks like for this material. And although I would say it's tenuous at this stage, when you're analyzing this data or taking these measurements late at night, your imagination tends to run a little bit wild. And what we noticed was that at the very highest fields, we always tended to get a bilinear-like resistivity. And then, of course, in the lowest fields, we started to get something that was a bit more B squared. We also noticed that as you go to lower and lower temperatures, your magnetoresistance becomes more and more bilinear. So, in case it's not obvious, this would be a lowest temperature resistance versus magnetic field curve. And these are isothermal magnetoresistance curves as you go in higher and higher temperature. But again, you only have a very small window of field to observe that linearity, and that's because HC2 is so high, and even for these materials, you need to go up to 65 Tesla just to get this data. So I would say it wasn't very convincing at this stage that there was any linear kind of behavior, even whether that's interesting or not. Okay, so we decided to take these same samples to the highest fields available in the world, which is up to 92 Tesla in Los Alamos National Lab. And what we noticed is that this bilinear-like behavior actually didn't seem to saturate at all. That's the highest fields available in our experiment, which is super high for those of you that don't know how these measurements are done. You need to essentially release about energy which is equivalent to about a case of TNT to get to these fields. Anyway, the point is that we saw bilinear-like resistivity up to the highest field. So we thought there was something very interesting going on here, maybe something that would connect to the T-linear resistivity. But again, quite tenuous at this stage. If that is true, then you might assume that if the bilinear resistivity is connected to the T-linear resistivity, then it's going to come into the form of one of these scaling relationships that you expect around a critical point. So in order to see that, what we did was that we would replot this resistance, but normalized to temperature versus the ratio of the field to the temperature itself. So by taking that ratio, you would expect to see some scaling form of the magnetic resistance as both a function of field and temperature, in the same way that you might expect scaling form around classical critical points. And this is what we saw. So this data here is exactly this data here. So this is just magnetic resistance versus field, and this is now this normalized form of magnetic resistance versus V over T, so the ratio of the two scales, field and temperature. And what we found was that all of the curves seem to collapse onto a single functional form. Well, that's the way to get it, yeah.
So rho naught that you're subtracting is field dependent?
This is very good. It is absolutely not field dependent.
It's not?
No, absolutely not, yeah. So this is a good point. This is the last time that you will see an offset like this, just to make sure that you know that we haven't fudged any data. Rho naught is the intercept from the T-linear part of the resistivity. So the basic idea is to subtract this elastic part of the resistance. So you only are looking at the temperature or field-dependent part of the resistance. And so that's the part. So this rho minus rho naught is only the what I would call the inelastic part of the resistivity, so the temperature and field-dependent part, and that's what you normalize to temperature. And you plot that as a function of V over T. But this is just to see that there is such a universal function. This is the last time that we will ever take any offsets. And that rho naught is taken at zero field and zero temperature. Okay. So there seemed to be a functional form, and that was already extremely interesting. And so with some help from some theorists in Tallahassee, we came up with an idea of what might be able to explain the scaling form. So first you begin with a simple analogy. So as I mentioned earlier, this business with the T-linear resistivity being associated with critical points is simply a connection between two energy scales, equivalent between two energy scales, namely h bar over tau and alpha kVt. Well, the equivalent relation with magnetic field would of course be to convert the field itself into an energy scale with some scaling factor beta. Beta just plays the same role as alpha in alpha kVt. Of course, this must be wrong at V equals 0, right? Because of time reversal symmetry, you always must have something like V squared resistance. But let's just take the analogy as it is. This would be what you might naively expect if you ignored any of your undergraduate training about magnetic resistance. Okay, so once we have that, now we want a scaling form because we can, of course, never get to zero temperature. This would be the zero temperature, zero field limit for both of these. But because all of our data is always at finite temperature and finite field, we need a scaling form that captures the relationship between these two variables. And that's where our Schechter became very valuable, because he suggested, well, what if you had a quadrature sum of these two energy scales? And this would capture a lot of the right kind of physics. So you can imagine at B equals 0, this just becomes T linear. At T equals 0, this just becomes B linear. But everywhere in between, it's always a competition for which energy scale actually dominates the resistance. If it is indeed only the energy scale that enters the transport. So that's the first the ansatz. And let's call this energy scale gamma. So this is the only thing you have to remember, that gamma is simply a quadrature sum of these two energy scales. Now there's a couple of things, if this is true, that we can answer straight away experimentally. The first one is, what is the relationship between beta and alpha? We don't have to make any assumptions about this, we can actually measure it directly. by taking the lowest temperature curve, so let's take T as close to 0 as we can get, which is 1.5 Kelvin in Los Alamos. And then take our highest fields, and then of course this relationship is dominated entirely by magnetic field, and then you can get the slope beta. So that's what we did. Here's the resistance versus KBT, and you can get alpha directly from that. Here's the resistance versus magnetic field, and you can get beta directly from that. Would any of you care to guess what the relationship, for those of you who don't know, what the relationship between beta and alpha actually is?
1 to 1.
Yeah, that's right. Couldn't be better, right?
The
Scale
very good.
this.
So in other words, your maximum B field,
Yeah,
the unit of temperature is like small.
exactly.
And what is it? Temperature?
Oh, temperature, it's about 60, it's about 1 Tesla is 1 Kelvin. It's a little bit less than that actually, it's 0.62 times.
But your linear resistivity being measured up to 700 Kelvin or 25, okay, you already see that.
Yeah, that's right. So you can get up to 300 Kelvin, which is about 25 MeV. But we can only get up to, well, actually this one's actually only up to 62, so we haven't done, I don't have 92 Tesla data. But it's the same, but yeah, so 62 takes you to about 60 MeV, but then it's 0.6 of that to get
Yeah, I get the same point, the horizontal scales and the vertical scales and the two plots are that is much reduced.
Totally agree.
Yeah.
But as I said, like we took this up to 92 Tesla and it's the same linear slope.
Sure.
But with the best, this is the best that we could do for the fields that are available. But even so, like there's no, I would say there's still really no fudging this, right? Like there's not very many other linear slopes of that data that you could take with a really different slope.
But, I guess what I'm getting at is you're really
It's a much smaller window, yeah.
relatively in the weak field.
If you can bring me a 300 Tesla magnet, I would very happily use it and take this even further. But we've taken it pretty much as far as we can, which is up to 92 Tesla, and we get the same slope. Okay.
Question and a comment. You have 5 more minutes. And the free direction is
Oh yeah, this is good. This is a good point. Right, so the current is applied in the AV plane, and the field is perpendicular to the AV plane. Yeah, so it's in the transverse direction. Okay, that's all I need. Right. So let's now forget about this business about subtracting offsets. Let's just plot the data as a function of gamma now. Right? We know what alpha is. We know what beta is. We can replot everything. But now, I'm not doing it as a function of temperature. We can plot it as a function of gamma. What I've shown you here is the same resistivity curve that you saw in the earlier slides, except now I've got a zoomed in version in the slower panel. But this is the zero field version, which means that gamma is just equal to temperature. Did you hand up?
No, sorry.
Oh, okay. The next line, I'll just show you what the T-linear extrapolated line is. So you can see that there is some deviation from T-linear behavior at the lowest temperatures, which is what the zoomed in version shows you. And now in this next slide, I'm going to show you the magnetoresistance. Again, no fudging, just the resistance as a function of field, but now plotted as this new scale gamma. And this is what happens. All of the resistivity curves as a function of field and temperature tend to appear to asymptotically approach this linear line, which is just a statement of the fact that the bilinear resistance is the same coefficient as the T-linear resistance.
These are different temperatures?
Exactly, yeah. So that's how you know that it's the real deal. So here, this would be it's a resistance versus magnetic field curve taken at 60 Kelvin, right? So as a function of gamma, at zero field it starts at 60, and then it goes up as B increases, even though T is not increasing, right? And it's the same thing for each one of these curves. And they all, it's as if they know that there is some asymptotic limit to the maximum resistance per unit, not temperature now, but per unit energy. Okay, so let's go to some other dopings. Here's one that's a little bit more overdoped. Again, apparently almost the same thing happens, maybe some deviations at very low temperatures, but certainly at these intermediate temperatures and fields, you get the same kind of asymptotic behavior approaching this T-linear line. Okay, again, even more overdoped, similar kind of asymptotic behavior, but maybe because you're a little bit further away from the critical point, you never actually quite reach this group line. But the point is that this was extraordinarily curious. All that we've done the minimal, we wanted to think about the minimal analysis to achieve this. And this is really the minimal thing that you can do. Just replot the data as this new energy scale, and you see all of the curves tend to approach this, this T-linear line that we're familiar with from the zero field behavior. Okay, so now in the last couple of slides, let me tell you a little, maybe some possible extensions of this physics to other materials. We're of course not physical to measuring meteor transport, it turns out. So we looked into the literature and we found this material. This is the equivalent to the ytterbium rhodium-2 silicon-2, except it's being doped with lanthanum so that the critical point is now at zero field. So I took the data, just the data feeding it, and plotted it as a function of temperature. They had it offset in their data. And now I'm going to perform the scaling relationship instead of resistance versus temperature. I'm going to do resistance versus gamma. And for a specific choice of beta over alpha, you get the curves to collapse on each other again, again in a similar way. I'll get to why this value is different. This was one, don't forget, in our previous slides. Okay. Another one, LSCO. So Nigel Hussey had done some beautiful measurements back in 2009 of magneto transport. You can see already that it's actually very strongly bilinear just from the resistance versus field curves. But I wanted to know, and these are field curves at different temperatures. So I wanted to know what happened as a function of gamma. This sample is slightly away from the supposed critical point, but let's see what happens anyway. Again, apart from perhaps the very lowest temperatures, where it's possible you're crossing over into one of the energy scales, for most of the curves, and these are just the same, it's just the same data with no offsets, just plotted in a different way, they all seem to approach this T-linear line that you're familiar with from the zero field behavior. So it's remarkable. I hope it's correct, but it's certainly true from the data. Like whether this is the correct interpretation is one matter, but the data certainly does has this kind of scale. Okay, which brings me back to one of my earlier slides, which was Andy McKenzie's suggestion that maybe there's some kind of universal scattering rate for temperature, or maybe what we're seeing for materials near quantum critical points, if that is indeed what's going on, is that actually it's a universal scattering rate per unit energy. And then you just need to convert the right variables to energy rather than just looking at them individually as a function of temperature alone. You'll see very similar relations, for example, if you looked at scattering rates versus omega. It's photoemission people do and people in optical conductivity do, that you'll see that a lot of relations like t squared plus omega squared will come up. But here we just have a t squared plus b squared. All right, let me tell you a little bit about, I think I have probably 1 minute or something. Less.
Take 1 minute.
Okay. So I tried to time it correctly, but anyway, the point is that my suspicion is that it's something to do with the Zeeman-like energy. I don't think this tells the entire story, but it certainly fits with some of the data. So if you just took out alpha from this relationship, then you just end up with the G factor as being the prefactor for this energy scale. Well, for alpha over beta is equal to 1. That would suggest a G factor of 2. And the G factor of this material has been measured independently and it turns out to be 2. Recall for ytterbium rhodium-2 silicon-2, alpha over beta was 1.5. Well, it turns out that would approximately correspond to a G factor of about 3.5. And if you actually measure the G factor of this material independently in this field configuration, it turns out its G factor is also 3.5. I think it's a little bit more than numerology. I think it's suspiciously interesting. Okay, so I had some new stuff about Hall effect. If you're interested in this T-squared versus T-dichotomy, but I'll just skip that. Just thank my students, Ian, who drove a lot of this physics, collaborators in Los Alamos and the National Hypergate Field Lab, Hardy and Ross, and then finally, from the people at Berkeley, happy birthday. Right. So we've worked very hard to do this. There is one major problem, and that is HC2 goes from being 50 Tesla at field perpendicular to the planes to being nearly 85 Tesla for peak field in the plane, which gives you a very tiny field for which to measure bilinear resistivity. So that's been the problem to say anything reasonably about the gradient. Worried about the window is so small already, it's even smaller for different orientations. However, I can say that there are preliminary data suggests that there is actually a strong variation. So it's not that so the linear resistance gradient decreases as you tilt the field out, even though the field is still perpendicular, which would argue against this G factor right here. So it's not just a local spin, somehow it's sensitive to the anisotropy of the system.
Is it known that the G factor does not depend on the vector?
No, G factor is anisotropic, but it's not that anisotropic. Like, I think it varies by a factor of 1 or 5 for this material. So it's not as anisotropic as the Fermi surfaces.
So we are running very late. So the last
Yeah,
question.
sorry.
I'm not sure about linear, but in those semiconductors and topological insulators, which are always low,
Yeah.
you get a linear resistance
Right.
because it breaks into a charged pattern. I guess this is the common understanding. Here you see to show something that involves with the doping. Could this be?
It's possible. It would be, I think a remarkable accident. The energy scales match up so well, like the gradients themselves. So it's not clear to me that the linear gradient in that kind of model would match the T-linear gradient. That's a bit of a surprise. But there might be some interesting physics there. Maybe instead of puddles as a function of space, if puddles as a function of time. Something interesting like that.
Okay, so let's thank all the speakers.